Okay, so because I'm only here for today and I didn't see other talks, I felt a little bit odd to make a PowerPoint and lock myself in. So I'm glad I didn't, because given I didn't know what Jackie and Lars were going to talk about exactly. So I'm going to talk about some stuff related to that. There's so many colors to choose from. My interest in, and you can interrupt me anytime, my interest in geotherms is, so I'm more at the surface part of the Earth. Here's temperature, here's depth, and when we think about geotherms, are we thinking something like this? I'll skip the core. Core is down here. Or is it something like this, okay, where you don't have so much of a strong lower thermal boundary layer, in which case that would imply you have more internal heating in your system. As Lars showed, there's stuff that can go on within the mid-mantle at around 660 and 410. There are phase transitions, and with the latent heat effects, you can have some kinks in the geotherm there. But we also know that because of the phase transition 660, you can make the conduction here sluggish. On top of that, the viscosity of rocks increases with depth. There may be one also increasing with just the phase transition. And anytime you increase viscosity, you increase the resistance to flow, so things flow slower. And as Lars said, when we're talking about temperature and heat transfer, there's conductive and advective. And if the conductive can catch up with the advective part, then you're not going to be adiabatic. And so there's a possibility, and this has been, we've talked about this for many years, right? That there could even be a little bit of a boundary layer there, and then it goes down to here. And so trying to determine this structure, the thermal structure of the Earth or any planet, is really about trying to get a whole bunch of pinning points here. And what I'll talk about is pinning points in this region, the zoomed in region. And when we talk about temperature up here in the boundary layer, temperature laterally can vary enormous amount from subduction zones, which are very cold. You can still define the potential temperature there, just artificially move it up, decompress it to the surface, and it would be cold. It could be 600 degrees potential temperature at the subduction zone. Is that what we're interested in? Because that can vary everywhere, right? Or are we interested really in what is the average temperature of the upwelling portions of the Earth? So the upwelling portions would be, at least for a planet where we have a mobile lid, the things of interest would be right here where the mantle is upwelling passively, and if you can get that already will tell you a lot about the thermal state of the Earth. And then we also have, and I'm sure you've followed some of this, especially with Don Anderson stirring the pot there, that if you have some interplate magmas, are they hotter? Are they hot spots? Are they hotter than your ambient mantle here? And that's important. What is the difference between these areas? Because if it really is hotter, and hotter means more buoyant, lower density, more buoyancy, then what these are focused upwellings that could come from would inevitably imply that you're destabilizing a lower thermal boundary layer. Whether that's from here or from here, you can't a priori tell just from the temperature difference. But so my interests in this are several. One is we still maybe don't exactly know that there is a difference there today. We would like to know that. There are uncertainties. I'll talk more about it. Lars says the solution is from the surface, and I would like to think that is the solution, because that's what we do. But there's some pitfalls there too that we can talk about. And then the other one is, as you go back in time, how does that difference change? What is the absolute? So if you looked at time, that was the Hertzberg and Rudnick paper, potential temperature, and again, you have to define what you mean by where you're talking about here. Presumably, we're talking about the mid-ocean ridges, so that today you know where they are, but you go a billion years ago, you don't really know. You're looking at a rock that's all jumbled up. You don't know the thickness. You have to do other things to get it. And so you want to plot all these up, and of course the curve, the way this curves, is it this, which is your traditional parameterized convection solutions, or is it something like a Cornaga style or Asian Nordic style, where you have some stagnant lid regime for whatever reason? And then, so you want that, you want the average, but you also want, so today, if this is 1350 potential temperature for the mantle, mid-ocean ridges, and you go to hotspots, are we at 1600? So you can plot those there, okay? And how does this change as we go through the planet? Do they converge, or do you have these so-called plumes that are also anomalously hot compared to the ridges? Okay, and that's important because if with radioactive decay, if you have higher, since it dies with time, the reactive heating is much higher back in the past, and it is not inconceivable that the shape of your temperature profile, like today, where you have a double, two strong boundary layers here, may be more like this, where you have a weaker thermal boundary layer and the plumes don't show up as much. And I don't know the answer, but we can talk about how we get that. Okay. So, any questions on that? Those are my interests. Oh, the other reason why that it's very important to know what the temperature is that if you know the thickness of the boundary layer for continents, and you know the temperature of the mantle, then you know their average effective temperature distance, which tells you something about the average buoyancy difference, and that dictates everything about the elevations of continents, which then tells you a lot, or has implications for climate and weathering and all of that, which I know we're not talking about here. But this is one way to tell all the surface people that the most important thing is us in the deep Earth, because it really controls everything about the continents. Okay. So, and I had one more thing. So what I really want to focus on is really getting these potential temperatures. But as you zoom into here, the boundary layer part, that's the conductive lid. The lithospheres, the strong part is in the thermal boundary layer. And when petrologists often talk about geotherms, they're actually talking about the temperature state in the conductive lid. And that's very interesting for us, but for whole mantle dynamics, history of the Earth, it may not be so important. The only time where it becomes important is that lower bound at the base of your conductive lid, if you actually know what the base is and what that tells you about in terms of the mantle potential temperature. Okay? So I will touch on that at the end if there's time, but I'll focus more on temperature of the mantle. So to get the temperature of the mantle, we have to recognize that, so I'm zoomed in now, that you have to have something to measure from a petrologist's perspective. You got to touch something and measure it. And if this is the solidus, so we're shallow enough that it hasn't bent around. We have a pinning point today, which is nice, about 25 degrees. See, that works. Although early in Earth's history, it may have been hotter at the surface. And then it gets hot in the convecting part of the Earth, so it's going to do something like this. And at a ridge where you're extending very fast, these are fast-spreading ridges, you do something like that. You advect all the geotherms or isotherms upward, bring this hot mantle. This is the solidus. Okay, this is the liquidus. Okay, let me erase these. And so the mantle at depth because the melting point increases with pressure. The mantle at depth is really a solid, although it behaves like rheologically as a fluid, so it can flow. And as you bring it up, if you bring it up fast enough so it doesn't lose its heat by conduction, it crosses the solidus, and then it melts. And then somehow, magically, the melt gets to the surface and forms a volcano, or the mid-oceanic ridge, or the crust. But when it gets to the surface, so let's say we'll just take this potential temperature today, it's 1350. When it gets to the surface, it is not 1350 degrees. We've never measured a basalt that's 1350 or even 1300 degrees. They're usually 1200 or less. So what happens is, of course, as they go up, they cool, because they're reaching the surface of the Earth. They cool, they crystallize, they even change their compositions. So when they really hit the surface, they're over here, or when they erupt, like that. So 1200 degrees, 1100 degrees. On top of that, as they come up here, as Lars showed from McKenzie and Bickel, when you're rising up, you're going under a phase change, solid-liquid phase change, so there's latent heat that's consumed. And so you can't actually stay at the same temperature. Some of that energy is going in to break bonds to generate melts, so that if you rose adiabatically, then the melting adiabat actually takes you off in this direction. Does that make sense? And this part is associated with the latent heat effect that you get there. And then the melts get close to the surface. They cool conductively. So once you start cooling conductively, it's kind of irreversible. You cannot play with these thermodynamic equations so easily. And so the challenge for the petrologist is to go back from here and to get this thing. That pretty much summarizes everything what we're trying to do. And it sounds fairly simple, but there are some complexities to it. So the first step was, one of the approaches was this McKenzie and Bickel, is that if I draw this thing again, there's too many lines on that. Here's solidus and liquidus. That this is where you have no melting, so 0%, and then the melting degree increases this way, so this is 100%. Okay, this is no different than looking at a phase diagram at one pressure, and here's temperature, and say the mantle is here, and you heat it up, and you go there, and eventually go from 0 to 100%, and it's there. It's not linear, but for simplicity, a lot of the early work considered it to be the melting was linear. And then what you do is, if you can get the melting degree of the oceanic crust, the basalts, which you can determine from the chemistries. We won't get into that unless you want to later, but some incompatible elements. You can figure out what F is. And if you know F, so this is different F's, and you have some model for how you are, what the PT path is in a perfectly adiabatic condition, closed system, then you can solve it. And this is what McKenzie assumed, that as you move up, that the melt always stays with the rock. It's a model, after all, right? And you try something else, it'd be much more complicated. So it sticks with, the melt always sticks with the rock, even though we know these melts keep escaping because they're low buoyancy and they go. And so once you can do that, you have this F, and you have this model, and there you go. You'll have a series of these adiabatic decompression curves, and as they come up, they will intersect all these F's, and you get the F either from melting, from the geochemistry, or you can get it from the oceanic crustal thickness, and that's what McKenzie did. And it depends a lot on this, the actual melt productivity, which at the time wasn't that well refined. It depends on where the solidus is, where the liquidus is, depending on what rock you're melting actually is. Are you melting a peridotite, or you're melting a peroxide, and so forth. So a lot of things can potentially go wrong. Now he used a peridotite, and he got, I don't remember exactly, about 1300 degrees. Maybe earlier he had 1250 or so. Okay, so that's one way. And any questions on that there? Okay. The other way is, well, how about if we could actually get this point itself and measure the temperature and the pressure directly? And so that's where it comes down to petrologists developing thermometers and barometers. For the most part, people were developing thermometers. A classic thermometer, it's just really the partitioning of some element between the melt and the rock. It's like, and how that partition coefficient varies with temperature. It'd be like my affinity for the beach, how it changes with temperature. Right now in Houston, it's so hot, and my affinity for the beach is very high right now. So this would be like for olivine. This phase diagram, simple stuff. And you don't need to know much that there's a curve here, and it's not the same with temperature. And so that you can use something like this effectively to get temperature if you have the right phase. And so the mantle we know is olivine, mostly olivine. It's got pyroxenes in there, but everywhere on the solid disk, at least in the uppermost mantle, it's olivine. And then for a long period in the fractionation process of the basalt, olivine stays on the liquidus. So as long as olivine's there, you can get temperature. And so that's what you do. It turns out magnesium is very sensitive to temperature. So the magnesium content of olivine saturated basalt gives you its actual temperature of that basalt right then and there. There's some complications with the amount of water or CO2, but when we're looking at mid-ocean ridges, you don't have to worry so much about that. So it gives you the temperature. Okay? But it gives you the temperature of the basalt itself. And so then what the petrologists have to do is they have to reproduce what nature did or God did with your basalt because it's crystallized. So you have to reverse the whole process, and you have to add the olivines back in until you reach the primary magma. And that's a whole can of worms of what the actual predicting what the primary magma is. But we don't need to get into detail on that unless you want to. So the thermometer right there is essentially the magnesium exchange between olivine and then the olivine component in the melt. That's right there. And then the other thing you can do is get pressure. And pressure has to use a different type of reaction. It's a reaction that actually involves generating new phases, and it's the olivine plus melt, which is silica, and OPX, okay, orthopyroxene. So it's using another type of phase diagram, which is this is olivine, OPX, and quartz. This is why you know. So the mantle is somewhere in here between olivine and OPX. This is why you know there's no quartz in the mantle. And when you hit the point like there, you have this reaction: olivine, the orthopyroxene breaks down to olivine, silica. It's a paratech reaction, and it turns out that as pressure changes, this thing moves around, and so it becomes sensitive to pressure. So you take these basalts, you try to get the most primitive one, and you back calculate to their primitive composition. You track magnesium and you track silica, and from that, it's a little simplified, you can estimate the effective pressure and temperature of that basalt from where it came from in here. So it's an independent constraint, and you get this. Sort of a little bit independent of having this adiabatic model. There are some assumptions there. In terms of the basalts coming up, after basalts rise, they hang out and have a party in a magma chamber, and then they show themselves to you, and you're sort of pretending that party didn't happen. But anyway, when you do that for the mid-ocean ridges, you get around 1350 degrees C. And most of the thermometer and most of the papers, all of us in the last 10 years that have been doing this, get this number, including Hertzberg. Okay. What time is it? When do I end? Oh, okay. All right. Then, okay. Well, let me. I don't want to bore you with the details of all the thermometers, but maybe I should say something about, because I'm sure you followed some of there's controversy from, even though he passed away last year, Don Anderson, the controversy over temperature. So here we talk, well, we know hot spots are hot, but if you talk to Don Anderson, he would always say, well, how do you know? And I don't know how much you guys have followed on that. Like, what is the problem? What's the deal? Is that, or you guys don't care on that? But, and the reason is that he suggests, or says, could it be possible, so here's the melting point, and for peridotite, but if there's some peroxenite in there, the melting point is actually much lower there. And you can be quite productive because the melting point is lower, so you can have pretty thick crust there. At the same time, as I told you, when we have to do we never get the primary magma, we have to reconstruct it, and we have to ignore that party. And if we don't do that, is it possible that these peroxenite melts can actually masquerade as something, and we've overcorrected most of our magmas? That's basically what he was fighting against for the longest time. So when it comes to the mid-ocean ridges, I don't think we have this too much of a problem, because we've developed other tools to determine whether you're melting peroxenite or not, sort of the fingerprinting, so that's okay. But when you get to looking at magmas in rift, continental rift environments, subduction zones, or back through time, this uncertainty becomes bigger and bigger and bigger. Okay, so I think I can end there. Unless I can keep on going, but.
That's a very helpful review of the potential temperature question. So we do have at KITP kindly provided us with a coffee break. We even have cookies from last night. So we could continue the discussion at the coffee break. And also at the end of the morning session, we have a half an hour time. We can continue the discussion. So I know people really like to go to coffee usually.
Yeah, I did. I knew that. I didn't want to cut into that.
Let's move to the coffee break and resume here at 11 o'clock. And we have two more talks, one by Thong Lei and one by Xi Jiezhong. And then we have a discussion before lunch. Please come back here at 11 o'clock.